Hi, I'm Ryan White. I'm a graduate student in the Bernien Lab at the University of Chicago. Our lab thinks a lot about quantum computing, quantum simulation, that kind of thing. These ideas have been around for almost 100 years now, and it's a new paradigm of being able to compute and calculate, simulate, explore new science using individual pieces of quantum matter. We are building our own quantum computer based on individually trapped rubidium and cesium atoms, and those are our qubits. And then the way we control those qubits is using lasers. So it's all very high precision work, and it's important to have good control of our lasers. I want to help develop new technologies for quantum computers. I'm hoping by the end of my PhD we can maybe demonstrate some exciting things with regards to quantum distillation or quantum error correction. Whereas a classical computer, the data is stored in bits, so either a 0 or a 1, quantum computers use qubits. You still have your 0 and 1, but they can be in any combination called a superposition. So you could have 50% 0, 50% 1, even with some complex numbers. So it's like a two-dimensional space. And because you have this greater density of information, you can really explore problem spaces faster, and that sort of gives a speed up to quantum computers. There's probably around a dozen or so lasers in our lab. We use lasers to trap our individual atoms, which are the qubits. And specifically, the qubits are in the electronic and nuclear states of the atoms. And to access those different states, you use more lasers for those. You have more lasers to cool down your qubits to the ground state. It's important to have very cold atoms as your qubits. So all of this manipulation is done by lasers. The frequency of the laser determines its energy, and that determines which states you are able to access in your qubit. And you want to access those states very precisely. And if your laser's temperature is drifting, that tends to cause a correlated drift in the frequency of the laser. So if you want to keep everything steady, keep everything precise, you need to have your laser at a steady, fixed temperature. The PolyScience DuraChill is doing a great job for us. We just fill it up and press start, and it's been keeping our laser at a steady temperature with no issues. We have a Sierra Matisse TISAF laser. That's one of our newest lasers in the lab. Very powerful laser, which also generates a lot of heat. So in order to keep that heat at a manageable level, we use the DuraChill chiller to maintain a steady 20 degrees Celsius. Acoustic vibrations are another source of potential noise for our lasers and for our experiments. So having something small that we can sort of hide in a corner, something quiet so that it's not rattling all around, is very nice. Something with a steady flow of coolant and a stable temperature. Those are the key points that we look for in a chiller. And the PolyScience DuraChill does a great job in both of those regards. Lots of ideas people have for quantum computers. They can solve certain classes of problems much faster than classical computers. They have the potential to break certain encryption systems that we use on classical computers. And they can even have new forms of encryption which can't be broken otherwise. It's also just useful in general for looking for solutions to these problems, maybe for developing new batteries, trying to get better energy efficiency. There's lots of potential for quantum computers to optimize things for the better. For me, it's being part of a community that's doing lots of exciting new science. There's not just quantum, but there's all kinds of exciting research going on here that I'm glad to hear about and learn about.